Chicas, pueden empezar en 3, 2, 1. Habiliten cámara, ya estamos en directo.
¿Cómo, Andrés?
En la actualidad,
Buenas tardes a todos y todas. Es el día 2 del ciclo de conferencias Explorando el Futuro. Mi nombre es Isabela Omen y mi compañera Valentina Solano. Los estaremos acompañando en la jornada de hoy. Además, agradecemos también a las organizaciones que han hecho posible este evento. A IESEC, las ramas estudiantiles del IEEE y los capítulos de AES de la Universidad del Cauca y la Universidad del Norte. Finalmente, agradecemos también a todos los colaboradores que han aportado de diferentes maneras a la construcción de este evento. Aclarando que el día de hoy tendremos la ponencia en inglés. Por esa razón, la información general será dada tanto en inglés como en español. El ponente del día de hoy nos ha confirmado que el tema de la ponencia no contiene lenguaje muy especializado. Por esa razón, es fácil de entender para todo público. En el programa del día de hoy contamos con la presencia del ingeniero Walt con la conferencia Spacecraft, Avionics and Scientific Instruments for Unmanned Space Missions, la cual es acerca de la variedad de dispositivos y sistemas en naves espaciales, desde grandes satélites hasta los nanosatélites, con ejemplos de misiones realizadas por el Southwest Research Institute.
Good afternoon to you all. It is day 2 of the conference cycle Exploring the Future 2020X. My name is Valentina Solano and my partner Isabela Omen. We will be accompanying you today. In addition, we also thank the organizers who have made possible this event, IESEC, the IEEE student branches, and the AES chapters of the University of Cauca and the University of Norte. Finally, we also thank all the collaborators who have contributed in different ways to the construction of this event. In today's program, we have the presence of the engineer Walt with the conference Spacecraft, Avionics, and Scientific Instruments for Unmanned Space Missions.
Walt Downing es el vicepresidente ejecutivo y director de operaciones del Southwest Research Institute en San Antonio, Texas. Esta es una organización independiente sin fines de lucro que realiza investigaciones por contrato en ciencias físicas y desarrolla tecnologías innovadoras para el mejoramiento de la humanidad. Desde su fundación, en 1947, la misma se ha convertido en una de las principales organizaciones de investigación aplicada y desarrollo del mundo. Walt es el presidente del IEEE Aerospace and Electronic Systems Society. Es miembro senior vitalicio del IEEE, evaluador del programa de ingeniería IEEE ABET y miembro de la Sociedad Honoraria de Ingeniería Eléctrica IEEE Eta Kappa Nu. Es el vicepresidente de la sección Lone Star de el IEEE en la región 5. También se desempeña como coordinador de relaciones gubernamentales para la región 5 del IEEE. Walt participa activamente en una variedad de organizaciones cívicas y grupos sin fines de lucro. Está en las juntas asesoras de la industria de la Facultad de Ingeniería y la Facultad de Negocios de la Universidad de Texas en San Antonio.
Walt Downing is the Executive Vice President and Chief Operating Officer of Southwest Research Institute in San Antonio, Texas. SWRI is an independent non-for-profit organization conducting contract research in the physical sciences and developing innovative technologies for the betterment of humankind. Since its founding in 1947, SWRI has grown to be one of the world's premier applied research and development organizations. Mr. Downing is the president of the IEEE Aerospace and Electronic Systems Society. He is an IEEE Life Senior Member and an IEEE Avid Engineer Program Evaluator. As a member of the IEEE Eta Kappa Nu Electrical Engineering Honorary Society. He is the Vice Chair of the IEEE Lone Star Section in Region 5. He also serves as a Government Relations Coordinator for the IEEE Region 5. Mr. Downing is active in a variety of civic organizations and not-profit groups. He is one on the industry of advisory boards for the College of Engineering and the College of Business at the University of Texas at San Antonio. Finally, I give the floor to Mr. Downing. Thank you so much for your intervention.
Thank you very much, Valentina. I will be making my presentation today in English. Do I need to pause for Spanish translation or just continue speaking?
Just continue speaking.
Okay, very good. Well, I'm going to share my screen, and if you could tell me if you can see it.
Yes, we can see it.
Okay, very good. Then we'll proceed. Very much my pleasure to be with you today to talk about a subject that I enjoy very much, and that is discussing the use of electronics in spacecraft avionics and development of scientific instruments. It's an area of interest of mine and an area of great activity at Southwest Research Institute where I work. But to begin, I want to introduce, again, this presentation is brought to you on behalf of the IEEE Aerospace and Electronic Systems Society, which is one of 39 technical societies in IEEE technical activities, along with 7 councils. And each society represents specific fields of interest. Our fields of interest are in complex systems that are used in air, space, land, and sea applications, including hardware, software, systems integration, and so forth. We're a medium-sized technical society of approximately 5,000 members worldwide, with over 70 chapters and a large number of student branch chapters around the world, several in Colombia. So we're very pleased to have good activity in the Aerospace Electronic Systems Society student branch chapters. The technical societies conduct many of the technical activities that are relevant to the IEEE as they're illustrated in this slide. For one thing, we conduct the technical conferences that are in each particular techno field of interest. So I think of perhaps interest to this group is our flagship conference in space, which is called the IEEE Aerospace Conference. It's held every year in Big Sky, Montana. So that it's in March, so that the participants can not only enjoy the technical papers and presentations, but also the skiing. Unfortunately, this year, due to COVID, the conference was held virtually. And another conference that we're very well known for is the Radar Conference that is held in different locations each spring. This year, it was going to be in Atlanta, Georgia next month. But again, it will be virtual again because of the COVID. But these are just 2 of many technical conferences that we conduct. Another thing that we have that's a very useful application for our students is our professional networking and mentoring program, where you can go to our website, you can apply to become a mentee to a more experienced professional in the aerospace field, and our society will connect you with a mentor that has similar interests so that it can help advance your career. We are also conducting virtual lectures. We often do these in person, where the society pays to send a speaker to perform a live in-person lecture at our chapters. But again, now because of COVID, we're conducting these virtually. We're in the midst of a virtual distinguished lecture webinar series that is running through the end of May. And so each week there are 1 or 2 virtual distinguished lectures. So I invite you again to go to the AESS website and see if there are any distinguished lectures that might be of interest to you. We do publications. For example, we have a monthly magazine. It's called Systems Magazine. This is a shot of one of the covers recently, and it covers not very heavily technical articles of interest to our professionals, but along with other announcements, interviews, historical articles, and those sorts of things. A very interesting magazine that's, of course, available online, but also delivered in print. And we participate in awards and historic activities. For example, this is an example of a Best Paper Award from our more recent 2019 radar conference with 2 of the members of our Board of Governors. This is a photo of our Board of Governors, or at least some of our Board of Governor members, taken back in the fall of 2019 in Cologne, where we had our meeting and we were participating in the unveiling of an IEEE historic milestone. And it was recognizing the first practical demonstration of radar on the Rhine River in Cologne. And here's Steve Welby. He's the executive director of the IEEE, also right here, and where he made the dedication of these plaques, one in English and one in German, for that recognition of that historic technical milestone. But if you look at the people that comprise our board, you can see we work very hard to have a very diverse and inclusive board with members from around the world of all different genders and technical fields of interest. We do only have one member right now from Region 9, and that's Layla right here, who's from Brazil. So she's our our Region 9 representative on the ESS Board of Governors. Now, as far as your local activities there in Region 9, we have a number of resources to support our local chapters. For example, we conduct summits where we gather together the leadership of all of our chapters in a particular region. The last one was again in Cologne, where we had our chapters from Region 8. And as a matter of fact, this is pictures from that summit in Cologne. These are the Board of Governors plus the chapter chairs from our chapters in Region 8, where we were talking about best practices, sharing ideas, those sorts of things. We pay to send the chapter chairs to attend the summit. We're going to have a virtual chapter summit next month in association with the Radar Conference, and it will be for Regions 1 through 7. We're very much hoping to have a regional chapter summit in Region 9 sometime next year. We haven't got a definite date, but we really would like to get to Region 9 and conduct one of these regional chapter summits. There are funding opportunities for our chapters. Each year for just ongoing type operations, chapters can apply for funding of $500 to conduct just normal meeting type activities and membership development activities. And then if there are interest in having major initiatives where you promote greater growth or other perhaps student activities, you can apply for funding typically between $1,500 and $2,000. And then we do a lot of recognition and guidance for our chapters. We have a Best Chapter of the Year award that's based on activities, and the prize for the Best Chapter of the Year award is $5,000, which really would fund a significant amount of activities. We have a handbook describing how to conduct chapter activities, and this is the URL for the chapter chair toolbox to organize and conduct local activities in the chapters. And then again, these educational programs, the distinguished lectures, which I mentioned earlier on the previous slide, as well as short courses. And these are opportunities where we send technical experts to our chapters to conduct a 1 or 2 day course that they can charge a registration fee for and raise money again for their chapters by offering training to local businesses or perhaps government entities on technical topics. And the society provides the seed funding to prepare the course, as well as the instructions, again, how to conduct the course. So there's lots of opportunities for chapters to essentially get their oh, start the video. let's see. So I guess maybe I wasn't sure that you were seeing that. So, okay. So those are the activities for the chapters. And let me move it to the next one. So in our technical fields of interest, we have committees or groups that we call technical panels, and they're in various fields of interest within aerospace. You can see radar and avionics and so forth. But again, perhaps a particular interest for you would be our Glue Technologies for Space Systems, or GTSS panel. And it deals with the technologies that are necessary for innovative systems based in space. So that might be broadband communications, software for networking, the Internet of Things, space networks, and so forth. And the panels are under the leadership of our Vice President of Technical Operations, who's Marina Ruggieri from the University of Roma in Tor Vergata. And our current technical panel chair is Claudio Sacchi, who's Associate Professor at the University of Trento. So if you're interested in participating in these technical panels, you can contact the technical panel chair. And then again, here's more information on that flagship conference of ours, the Aerospace conference that is held each year in Big Sky, Montana. And the next year it will be held March 5th through the 12th in Big Sky. The call for papers is out. So you can, and the abstracts are due in July. So if you're interested in perhaps participating in that conference, that would be a good opportunity. This is a really first-rate conference. As a matter of fact, a number of examples in my presentation are going to be from papers at this aerospace conference. We have publications in addition to the Systems magazine that I mentioned earlier. We have a peer-reviewed journal that we call the Transactions on Aerospace and Electronic Systems, and it covers, as I say, systems, including organization, design, development, and operation of these complex systems and these types of applications. And so you can see it would include topics as referred to before, like navigation, avionics, and so forth, spacecraft. These are the current publication statistics with respect to this peer-reviewed journal, and we've been improving these impact factors and other publication metrics year after year. So another opportunity, if you stay in academia, this would be a good opportunity for you to publish some of your research related to aerospace systems. And then again, the magazine, the Systems magazine, and now I'm going to be moving into the main topic of my presentation about spacecraft, avionics, and instruments. And a reason I've shown these three covers from the Systems magazine of April 2019, September of 2019, and March of 2020 is that this was a special series or special issues on the Artemis 1 Cubesat missions. Now, I'll talk more about this later, but Artemis 1 is a United States NASA mission or series of missions that are planned to return to the moon. And as part of these missions, there will be a number of CubeSats, which I will explain again in detail in my presentation. And so a number of my topics here come from these three issues. And again, I would point out that these magazines are free to AESS members. That's part of the registration fee. But what you see illustrated on the cover are some of the topics of interest. Like this is the first application of CubeSats outside of Earth's orbit. These were on the mission to Mars, and these two CubeSats here were used to relay telecommunications back to Earth. So it was the first CubeSats to leave Earth orbit. The communications are a really key issue with respect to CubeSats, and so we had a article or a series of articles dedicated to all the telemetry and deep space communications. And then propulsion is a really key issue for these small satellites, and so this was an illustration of a solar sail that might be used, and it's going to be one of the Artemis 1 CubeSat missions where they try out this sort of innovative propulsion technique for CubeSat. So again, this is sort of a summary, but let's go ahead and move into more of the discussion about space instrumentation, space avionics. So first thing I think to point out is that satellites are typically characterized or often characterized by their size. In other words, their payload mass. And And so you can see this diagram here, and these are not strict limits, but generally speaking, if the mass of or the payload of a satellite, the mass of the satellite is greater than 1,000 kilograms, it falls into this category of large satellite. Now, some of your very famous satellites are these large satellites, like the Hubble Space Telescope, for example, is 16,000 kilograms and about the size of a bus. And perhaps another famous one that you might be familiar with, the Cassini Satellite, that took all these spectacular images of Saturn. And recently, within the last 2 or 3 years, it ended the mission by crashing into the planet. It was a 6,000 kilogram satellite. So those are both very large satellites, very expensive, over $1 billion for the mission, many, many instruments, very complex. But as you start moving smaller, you get into this domain of medium satellites, say in the 500 to 1,000 kilogram range, and then a mini satellite, kind of using the same notation we often use in electronics. A mini satellite being 100 to 500 kilograms, microsatellite, 10 to 100. Then you go down sort of by decade: nano satellite 1 to 10, picosatellite 0.1 to 1 kilogram, and femtosatellite less than 1. Now, practically speaking, we really don't have satellites in this range yet, but it's possible in the future. But I talked about cube satellites, or I mentioned cube satellites earlier. Cube satellites are typically a type of nano satellite. They fall into this payload range, and it's because there's certain constraints on their mass and size factors. So CubeSats, class of nanosatellites, anything under 500 kilograms is considered a small satellite. And the purpose of these types of small satellites, and CubeSats in particular, is to reduce development and launch costs, and therefore you're not risking $1 billion on a single failure, single satellite. It actually facilitates the use of satellite constellations and swarms. So you may not have a single satellite that's quite as capable or carries as many instruments, but by using multiple satellites networked together with those glue technologies that I mentioned earlier, you can accomplish the similar missions at less cost, less risk. But of course, there are technical challenges associated with making satellites smaller and smaller. They include a lot of things, but one is that the smaller your mass, the less power you have. And it also gives you some real challenges with respect to propulsion. I mean, these large satellites here carried kilograms worth of propulsion to change their attitude, to change their orbit. Once you start getting down in this range, you have very little fuel that you could use to change the orientation, change the orbit of a satellite. But one of the things that's really important is that CubeSats and these reductions in cost and size and risk enables universities and others to conduct space research. It's no longer limited to just your national space agencies. And because you can participate, you can do not only scientific missions, but you can also demonstrate and mature technologies for future missions, much larger missions. And because they're small and lightweight, they are often carried as secondary payloads on larger missions. A number of CubeSats have been carried up to the International Space Station and launched from the space station, or they are carried aboard a large satellite type mission, but they're deployed separately along the way. Another thing that this allows is it supports private spaceflight initiatives. So you're having these organizations such as SpaceX, Blue Origins, and whatnot that are looking at opportunities to launch these very small satellites, and it's becoming, again, not simply the domain of large government agencies. It is a very rapidly growing segment of the satellite launch industry. So I'd like to go through maybe just a quick example of these, but again, most of my focus is going to be on these CubeSats. So here's a large satellite example. And all of the examples that I've chosen to show you today are missions that Southwest Research Institute, where I work, played a major role. Either as the principal investigator or the provider of a spacecraft itself, or an instrument or the control package and so forth. So these are all examples from work conducted at Southwest Research Institute. So this example is the Juno mission. It's a NASA New Frontiers mission. It was actually the second one. I'll show you the first one in just a second, but this was the second NASA New Frontiers mission. And you can see again, it falls into this large satellite example because it's over 1,000 kilograms dry mass. And when you added the propulsion, the total launch mass was 3,600 kilograms. So in that large satellite example, and I'll show you some pictures to give you an idea of the dimensions of it also. The purpose of the mission is it's a polar orbiter around Jupiter to study the gravitational field, the magnetic field, the magnetosphere, and the internal composition of the planet. Now, you know, Jupiter is what they call a giant gas planet, and they don't really know. One of the things they don't know is whether or not it has a core, a rock or metal core. And so part of the purpose of the Juno mission was to explore and see if you could determine if Jupiter had a solid mass core or if it was gas throughout. Another thing that's kind of interesting, well, the mission was launched in 2011 from Cape Canaveral on an Atlas V rocket. This is a picture of the launch. The Atlas V rocket is the largest rocket that the U.S. has in its inventory currently. Now the Artemis will be coming in as a large mass vehicle. And of course, we utilize other countries' launch vehicles occasionally, like the Russian Soyuz type rockets. But this again was because this was a large, heavy satellite. It needed and it was going a great distance. It needed a large rocket to get it on its way. Here's an interesting thing about it from an electrical standpoint is that this is the most distant solar-powered mission to date. You know, the solar energy out at the orbit of Jupiter is much less, obviously, than here on Earth. And so typically when you start getting that far out, you have to use another form of generating electric power. And I'll talk about that in a moment. But this satellite actually used solar power, and so consequently, the solar panels were quite large. It did arrive at Jupiter in 2016 and began its scientific mission. And because it's been collecting very good data and science, the mission has been extended through 2025. And so the Juno satellite, here it is before it went into its fairing for the rocket launch. And so you can see here's people to scale. So, you know, it's a 3.5 meters in diameter and 3.5 meters high. So it's a pretty good size satellite. It is a spinning satellite with fixed instrument mounts. So each of the instruments here are fixed in place. They're not movable or gimbaled. And the orientation of the spin of the satellite brings the field of view of each instrument into play during the mission. The command and data handling system, or the avionics, if you will, the heart of it is a RAD 750 CPU. Now, RAD means it's a radiation-hardened computer. It's got 256 megabytes of flash memory and 125 megabytes of dynamic random access memory. So you can see we do a lot with a little, again, but remember this satellite was launched in 2011, and which means the design began probably in the neighborhood of 2005. You always have to take that into account when you're dealing with these large space missions, that the technology that you have available when you design and build the avionics or the scientific instruments has to last a long time. The radiation environment is very, very strong in Jupiter, so having radiation-hardened electronics and protected electronics was very important. The telemetry for this satellite uses X-band and Ka-band. That's how it delivers the control and attitude control type information, as well as the science. But then here's an interesting point. Again, the radiation field is so strong at Jupiter that the instrumentation, the delicate electronics are enclosed in a 200 kilogram titanium vault to shield it from the radiation. So that was a significant portion of the payload. And you can see the solar panels, which are being tested here. This is one solar panel with the magnetometer boom on the very end. They extend out 20 meters from the body of the satellite. So pretty large object once you got it deployed. And then you can see that to get into the fairing, these solar panels had to be folded up. This is the solar panel right here with the magnetometer boom. And so you can see it all has to fold together to fit inside the fairing of the rocket. And then it has to be able to reliably extend out when it's deployed for the space mission after it gets out of the Earth's gravitational field. So this is sort of the mission. So one of the things that's very interesting is that, as I'd mentioned, it's a polar orbit in Jupiter, around Jupiter, and it's a very elliptical orbit. You can see it swings in close to the planet, zips by, and swings way out. And it's a stationary orbit, and the planet is rotating beneath it. So each time it swings by the planet, it's taking pictures of a different portion of the planet because the planet's rotating underneath it. And so again, using those fixed instruments, spinning with this highly elliptic, and part of the reason for the highly elliptical orbit again is to limit the amount of time that the electronics have to be exposed to that high radiation field. It's got a lot of instruments. You know, the thing that you always see when you hear about a space mission are the pictures. So it's got a camera, the Juno cam, and it's the one that's been sending back very spectacular pictures from Jupiter. If you've seen polar pictures of Jupiter for the first time, pictures of the red eye, pictures of very large hurricane strength or even higher winds, you know, so this gets obviously a lot of publicity because the images are very spectacular. But it's got a lot of other scientific instruments on it as well. I mentioned earlier that one of the things that they were very interested in learning about was the interior composition of the planet, and they're doing that with a microwave radiometer instrument, and it does kind of like slices, almost like a computed tomography type approach to looking at greater depths into the planet. And kind of each slice of this radiometer instrument allows you to tell something more about the density and of the interior parts of the planet. There's almost always spectrographs like ultraviolet. This instrument right here, this ultraviolet spectrograph, is one of the instruments that Southwest Research Institute actually provided for this mission, and it's able to detect radiation or ultraviolet radiation that is often provided by charged atoms, like helium atoms, for example. So you're able to get, this is an image from the ultraviolet spectrometer of sort of a corona effect around the pole of Jupiter using this UVS. I might mention that in addition to providing this instrument for the Juno mission, the principal investigator or lead scientist, if you will, is Scott Bolton, and he also works at the Southwest Research Institute. Another thing that's often used when you as instruments when you're on these missions is particle type energetic particle detectors. So here's one, an energetic particle detector, and as a matter of fact, an auroral mapper and a plasma waves instrument, and of course there was a lot of interest in the magnetic fields at various locations. So you've got a flux gate magnetometer, which has to be located as far as possible from the mass of the satellite to avoid interference from the mass of the satellite. But you can see, again, large satellite, many instruments to allow you to study the composition and the magnetosphere, or the magnetosphere around the planet Jupiter. So that's a large satellite example. So here's a medium satellite example image. This was the first principal investigator-led mission in the U.S. It's a few years ago. It was back in the year 2000 when it was launched. The principal investigator is Dr. Jim Birch, who's the vice president of our space division, Space Science and Engineering Division at Southwest Research Institute. So medium satellite, as I say, just a little over 500 kilograms, so it's on the low end of that medium satellite scale. It's also a spin stabilized satellite, and the mission was it was the first mission to image the magnetosphere around the Earth. First one to image the Earth's magnetosphere, but it did it from a single point, again, spinning satellite, and I'll show you some images from that. It was basically designed to allow you to study the interaction of the Earth's magnetosphere with the solar wind and the charged particles and the plasma and hot gases flowing from the sun. So it launched from Vandenberg in March 25th of 2000. I was at the launch launched on a Delta rocket, and it's in a geocentric polar type orbit. It's low powered, much lower powered, 286 watts and it's solar arrayed. You can see in this case it didn't require large wings, but you've got solar arrays located on the top, bottom, and sides of the satellite. It also needed a radiation hardened CPU, but a little bit more less power. This is an earlier version of the one that you saw on the Juno mission, and it uses it's not as far out, so it was using an S-band transponder for the control and the telemetry. So this mission's complete, and the satellite is actually, they lost contact with it after the mission was complete in the 2005 timeframe. But it did accomplish its mission. It did get the first images of, for example, these ultraviolet images again, or like of the aurora around the pole. It had 3 energetic neutral atom imagers of different energy, and it also had a radio plasma imager, so it could detect plasma. So when you used all of the instruments combined, you could get a good idea of the interaction of the wind with the magnetosphere, and kind of tie those together, seeing where it occurred and what types of ions and hot gases were in each particular segment of the image. So medium-sized satellite example. Now here's a mini satellite example. Now we're talking about a satellite under 500 kilograms, and this is the New Horizons mission, a very famous mission because it's the one that went to Pluto. And we had these very iconic images of Pluto as we flew by. So it was. I'd mentioned earlier that Juno was the NASA New Frontiers mission 2. New Horizons was New Frontiers mission 1, and the principal investigator on New Horizons this is still an ongoing mission, Dr. Alan Stern, who works for Southwest Research Institute in our Boulder, Colorado office. So it was the first flyby exploration of Pluto, and then it continued on an extended mission to explore a Kuiper Belt binary object called Arrokoth, and this is an image of that binary Kuiper Belt image. Now it's a lighter satellite than Juno, but it also launched from Cape Canaveral on an Atlas V, and there's the launch from Cape Canaveral. Again, biggest launch vehicle in the U.S. inventory, and it was not so much because of the mass, but it was in order to get to Pluto in a timely fashion, because they wanted to get there. They wanted to look at the possible atmosphere, and they wanted to catch Pluto at the right part in its orbit where the atmosphere would still be visible or detectable, and that meant they had to get there very fast. So when it launched and left the Earth's orbit, it was the fastest object ever launched from Earth. Even so, you can see the timeline here. Contract week began in 2001. It launched in 2006. Flew by Jupiter in 2007. So that's a very fast time, to go from Earth to Jupiter, and then arrived at Pluto in 2015. So it still took, 9 years after launch to get to Pluto, and then to take all these images. And then in 2019 did the flyby of the Kuiper Belt object. And it's still going, and they're looking for other potential targets for a continued extended mission. So here's the spacecraft, again, spin-stabilized satellite. It's triangular shaped, but much smaller, if you will, than these others. It's got a very high gain antenna because it's going so far out in deep space. A little bit less power than the image satellite, but notice that this one does not use solar arrays. It uses a radius isotropic thermoelectric generator, which is this device right here. So how thermocouples detect heat and generate electricity based on heat. Well, this is sort of the same process. If you apply heat, it generates an electric current, and so you're getting that 245 watts of energy that's generated by the thermoelectric isotropic generator. Now, thermal control, since you're going so far on deep space, thermal control is a major consideration. So you can see these thermal blankets that were used to protect not only from the cold that you experienced when you were out at Pluto, but also the heat when you were much closer in toward the sun. From a guidance and navigation standpoint, it utilized 2 star trackers and a sun sensor, as well as a dual inertial system. This one had propulsion and with 16 thrusters. And part of the reason for that is that, again, Pluto was so unknown and so far out, the exact location was not known as precisely as the location of closer in type objects. So during the course of travel to the planet, they had to make several different course corrections because they wanted to come by close enough to get really good images and information, because it's going so fast. It's sort of a trade-off. It's going so fast, you're not going to be able to stop in inner orbit. But that's the trade-off of getting there in time in order to at least make the first flyby observations. So they wanted to be close, but not too close. And furthermore, they didn't know when it launched how many satellites or how many moons Pluto might have. And so they did, in fact, discover additional moons that were unknown when the spacecraft was launched. And of course, they had to take into account any sort of guidance and attitude control to avoid those objects colliding with those objects. 2 redundant integrated electronic modules, because again, they were only going to have one shot at gathering the scientific instrumentation data. And the orientation of the satellite when it was making its science observations was different than the orientation it needed to be to deliver data back to Earth. So as it approached the Pluto, it had to execute a maneuver to put the instruments in position where they could view the planet. It recorded the data and then reoriented back to point toward Earth with the high gain antenna and delivered the telemetry data on time. I happened to be in this Space Operations Center, Mission Operations Center when it went by Arrokoth, and it's always a pretty exciting thing to see that data start coming in and know that you actually got something. Here's a block diagram of the New Horizons satellite. So you can see this is pretty typical of the way you break it down. You have a propulsion system, and here's these thrusters. You have a power and thermal control system that in this case, you can see where the power was generated by the radioisotropic thermoelectric generator, and then it's distributed to the power switching modules. It's distributed to the various command and control modules. Then you've got a guidance and control unit, and as I'd indicated, it has sun sensors and star trackers and inertial measurement units. And then the guts of it with the computers, the avionics with the command and data handling. And here you can see the solid state recorder where your instrumentation package, and these were the 6 instruments on the satellite, were delivering data. And as I said, it was dual redundant. So you delivered the data to 2 command and data handling packages, and then the RF communications with the high gain antenna to the deep space network. So pretty typical, and you'll see something similar to this as I show some further examples later on. So here's the New Horizons scientific instruments. There was a long-range reconnaissance imager, which took some of the really spectacular photos of Pluto's surface, and also that picture with of the planet that had what it looked like a heart on the surface. Then there's a solar wind around Pluto instrument, particle type instruments, and then a new generation of that spectrometer. And that spectrometer, UV spectrometer, again built by Southwest Research, took this image just after New Horizons flew by Pluto with the sun in the background showing the atmosphere. And of course, they were able to not only see the atmosphere, but they were able to get information with respect to the composition of the atmosphere. And so multispectral imager to get different things. So again, very highly complex satellite with a lot of instruments. But now we start getting into the much smaller satellite range, in this case, the microsatellite. So now we're talking about under 100 kilograms. And the example I'm going to use is not a deep space planetary mission like the previous two, but one that stays here in the Earth's orbit. It is called the Cygnus mission for Cyclone Global Navigation Satellite System. And it is a constellation of satellites. Again, I'd mentioned earlier, when you go smaller and lighter on these satellites, you can deploy them in clusters or in constellations. And so this was a 8 satellite constellation, low Earth orbit. And since it's much smaller and lighter, it was able to be air launched from a Pegasus rocket that was delivered from a aircraft in the air, and was the first. This is the first privately developed rocket. So again, I'd mentioned earlier how small satellite technology enables the development of missions or systems that are privately developed and not totally reliant on, so for example, government agency launch systems. This mission was recognized in 2017 as the Small Sat Mission of the Year at the Small Satellite Conference. The principal investigator was Dr. Ruff from the University of Michigan. Southwest Research Institute built the satellites and the controls, as well with participation from guidance and navigation from Sierra Nevada and Surrey. This is a picture of the 8 satellites on their mounting frame that would go inside the fairing. I think I actually have a better picture perhaps in a second. But again, the block diagram, very similar in a way to the one you just saw for New Horizons with the attitude and control package, the control and data handling type package, the transceiver for telecommunications, the thermal, mechanical, and structural package, and the electric power package, as well as and so forth. So same type of architecture in a way, but smaller and less expensive. For example, as I mentioned, in this one, Southwest Research actually built the space platform, and it's a microsatellite, and it's designed for payloads between 10 and 100 kilograms, and it's been selected for NASA's Rapid Spacecraft Catalog. These are solar powered typically, and consequently peak power tracking is very important. It uses a single board computer with data handling subsystems and telemetry interfaces. Low Earth orbit, so S-band communications, very simplified attitude determination control system, and like many small satellites, no active propulsion. The propulsion or the data, the attitude and orientation is by reaction wheels and torque rods. More about that in a moment. It is common with small satellites, and particularly cube satellites, that had just a single scientific instrument payload. It was a Doppler delay mapping instrument. And I'll talk about the purpose of this mission in just a second, but it uses a lot of emerging small sat component technologies at much lower cost than space-rated components. And that's a key element, again, in making these missions possible. So here's sort of the size and deployment idea. You get a size of the unfolded. These are the solar panels, and here they're actually folded for being attached to the deployment module off the Pegasus. And then when they got up into the to the launch area, they were deployed for a orbit around the Earth. And here's the configuration of that spacecraft bus, and you can see where different elements were located. And the computer data handling subsystem, that single board computer, very low power. And one of the things that's really key as far as avionics and instrumentation on space programs is what they call the flight heritage of the devices. You really would like to have proven technologies if at all possible. So this architecture on this particular computer was the same general architecture that was used on the Juno mission as well as other missions. And the interface for the companion data control was also used on multiple missions. So this is considered to be sort of a risk reduction approach, and you see that's really key in a lot of space missions. The electrical power system, subsystem with peak power tracking was again a single board thing, and I wanted to mention this one in particular because if you want to see more details about this particular card design, this was presented at that Aerospace conference that I spoke about earlier in 2017. So if you go and look at the proceedings of that particular conference, Aerospace conference in 2017, you can see a whole paper on this peak power tracking and electrical power subsystem. And it's been used on multiple missions, Cygnus, and some future ones as well, including one coming up here as a Cubesat. So attitude determination control system, it's a nadir pointing, in other words, pointing down toward the Earth, 3-axis stabilized. It uses a horizon sensor as well as star tracker, sun sensors, 3-axis magnetometers, reaction control wheels, and torque rods. And the way it maneuvers is it utilizes what's called a differential drag maneuver for spacing after it was separated. So by changing the orientation and attitude of the spacecraft, you could achieve separation into the constellation event. So what this constellation was doing, the purpose of it had to do with weather forecasting in the Gulf of Mexico. They wanted to better understand the speed of the wind at the surface of the water, being able to look through the clouds and see the speed of the wind at the surface. And the approach that's used, this differential Doppler type instrument on each satellite, uses a scintillation effect of the radiation off the water. And by looking at the GPS clock, you can see this difference between the reflected wave and the time from the clock, and there's calculations that essentially relate this Doppler shift with the speed of the wind, and that's essentially the approach they were using with a single instrument to look at this differential Doppler, and that's the purpose of this particular mission, the constellation of satellites doing periodic revisits over the Gulf of Mexico to give you better information with respect to the speed of the wind, which can plug into various hurricane tracking models to allow you maybe to better predict the size, the strength, and direction of the hurricanes in the Gulf. So our next mission for this particular space platform is going to be the Punch mission, which we're leading, and it's going to be outside of the Earth's orbit because it's going to look at the solar wind going from the sun, the corona, if you will, into the heliosphere. And it's going to use four microsatellite constellation, about 40 kilograms each, a little bit smaller. And each of the satellites is going to carry a narrow field imager. One carries a narrow field imager, and 3 will carry wide field imagers. And this mission is planned to launch in 2023. So again, reusing this idea of heritage and reutilizing space platforms to reduce risk. But now let's talk about nano satellites, and specifically let's talk about Cubesats. What are they? So it's a class of small research satellites, this nano satellite, less than 10 kilograms typically, that are built to standard dimensions, or U's, and each one U is 10 centimeters by 10 centimeters by roughly 10 or 11. It's roughly a cube-shaped dimension. And they're modular. You can have a 1U satellite, less shown here. You can have 2U's, which would just be 2 stuck together. 3U's, this is a 3U right here. 6U, which would be 2 3U's kind of connected together, or 12U. Now, 12U is sort of the practical limit. I mean, it's not a hard limit, but once you start getting beyond this, I mean, each unit is 1.3 kilograms. So you can see that once you get up to like 12, you're starting to exceed that 10 kilogram range for a nano satellite, and you start, reaching limits of what you can carry on a ride share and whatnot. The size and the weight become larger than these sorts of missions where you would deploy them. So it's not an absolute limit, but this is sort of the rule of thumb, because again, CubeSats are very typically flown as secondary payloads on larger missions, and I'll talk about one of those in a moment. They're dispensed from launch systems, typically along rails or tabs of a spring-loaded deployer. So that, again, you notice no propulsion on this, so it's launched. It's basically fired by spring launch from a deployer inside another mission. And I'll show you how that's done in a moment. Each year, NASA has, U.S. NASA has various launch initiatives, which are opportunities for small satellite payloads to fly on rockets planned for upcoming missions. And of course, they have a website for that. A little background on CubeSats. They sort of came into being back in 1998, 1999, when California Polytechnic State University and Stanford developed a CubeSat specification. Now, they were originally intended only for low Earth orbit missions, very short duration for scientific research or to explore new technologies. And academia, colleges and universities have accounted for the majority of the early CubeSat missions. But that's expanded now, and as I'd mentioned earlier with that image from the Systems magazine, in 2018, the Mars Cube 1, or MARCO mission, was the first mission to launch and operate CubeSats beyond Earth orbit. So here's one of those MARCO CubeSats right here. And as I'd mentioned, Mars Cube 1 was a mission to Mars, and these satellites were used to as relays to send telemetry data back to the Earth. So you can see how since the start, since 1998 and so forth to the present, over 1,200 CubeSats have been launched, and it's growing very rapidly. And that's as of January of 2020. So there's been more now, and you can see there have been some failures along the way. But again, these are often considered to be a little bit high. They're able to accept a higher risk and a failure because they're less expensive, and in some cases, since they're constellations, you might still have a successful mission even if you lost one or two of the satellites. So Artemis 1, that mission to the moon that I showed you when I was showing the Systems magazine, is the primary mission is to do an uncrewed test flight of the Orion multi-purpose crew vehicle, which is kind of illustrated here. Now that's intended to be the United States' next crew vehicle to do manned exploration of the moon. So this mission is to test. It would not be piloted by humans. It would be a robotic type test of this crew vehicle. It's scheduled to launch from Kennedy Space Center, and it's a 3-week mission. It will go to the moon. It'll be a translunar injection. It'll spend 6 days in a distant retrograde orbit around the moon, return to the Earth, and be recovered in the Pacific Ocean. That is the mission, the primary mission of Artemis 1. But in addition, Artemis 1 mission will carry 13 6U CubeSats. And this is a list of those CubeSats. These 7 were selected by various NASA directorates for missions such as looking for ice on the moon, or looking at the effects of lunar gravity on biological systems, or other things. And then 3 of the CubeSats were selected through a CubeSat challenge. And this is Explorer and Escape Explorer. And then 3 of the CubeSats are provided by international partners, Argo Moon from the Italian Space Agency, and then 2 missions from the Japanese Space Agency. And so these little symbols that I put next to each of the CubeSats, or several of the CubeSats, illustrate what issue of Systems magazine you can find more details about that particular CubeSat. So the little red asterisk would apply to Cusp and Lunar Ice Cube and these 2 Japanese missions. That appeared in the April 2019 issue. And then the little purple caret for these, and the little green tilde for these. So if you want to learn more information about any of these CubeSat missions, you can see it in Systems magazine. I'm going to focus on Cusp because, again, this is the mission that Southwest Research Institute is currently participating in. Now, the launch vehicle for the Artemis 1 mission is going to be the Space Launch System, or SLS. And here's sort of a diagram of it. So again, the primary function is to test this Orion multi-purpose crew vehicle right here. And you can see it's got a liquid stage along with solid rocket boosters, and then you got an adapter to connect you to the propulsion unit, which is used to send the first stages, put the satellite into Earth orbit, and then the interim stage is what sends it to the moon and back. But I want you to notice here, between this interim cryogenic propulsion stage and the Orion crew multi-purpose crew vehicle, there's a stage adapter. This is where the CubeSats will go, in this Orion stage adapter. And so I'll show you more about that in a minute, but you can kind of see where that will be with respect to the entire rocket. So here's that Orion stage adapter, showing between the first stage and the Orion crew vehicle. And then here's a picture of it. And you can see on the inside of this stage adapter, there are mounting points for those 13 6U deployers. And you can see this is sort of like a rail type deployer. So each of those 6U satellites will be fit in here. And when after the interim cryogenic propulsion stage sends the Orion crew vehicle on its way to the moon, this stage adapter is going to separate, and then en route, this stage will be what deploys those different CubeSats at different stops along the way. So here's the mission map. So the primary mission, you can see that it launches from Kennedy, goes into an Earth orbit, then does a translunar injection, follow the orange line here, goes into that distant retrograde orbit around the moon, and then after 6 days has a return with the purple line back for recovery in the Pacific Ocean. But notice right here, this after it does the translunar injection burn, and the interim cryogenic propulsion stage, or ICPS, separates from the Orion crew module, it continues on separately. And this dotted line here, it's no longer attached to the Orion crew vehicle, but it's continuing on because it's going into disposal, it's not returning to Earth. And then you see on this dash trajectory, there are points labeled A, B, C, and D. They refer to them as bus stops. These are points along that translunar injection orbit where the different CubeSats will be deployed. So that's, again, separate from the primary mission. So Cusp, the CubeSat mission to study solar particles, was one of the feature articles in that series. And so we're going to go into this particular mission, the Cusp mission, in greater detail, because it's, again, led by Mihir Desai. I want to thank him for his assistance in all of the details regarding this particular mission. But you can see, like many missions, it involves a number of players, including JPL, NASA Goddard, as well as NASA headquarters. So, what's Cusp? It's a NASA Science Mission Directorate. It was sponsored by the Heliospheric Science Mission, and it was designed to do research on space weather. Now, space weather is the electromagnetic storms and the solar particles and whatnot that are generated during very high events, solar active events. And we don't understand that very well because we can't necessarily observe it. So the notion of this particular mission was to be able to be a forerunner where you could put multiple small satellites out there to observe the solar weather and use it to better predict really strong solar storms that could destroy, damage things such as telecommunication grids, or even be harmful to astronauts that might be on the space station. So you want to be able to predict the solar weather, or space weather, if you will, just like you would be able to predict weather on Earth. It looks at energetic particles. They call them superthermal particles, and I'll show you more about that in a second. Another purpose into just understanding space weather is, again, to increase the technical readiness of instruments that you might put in these very small missions. And So that's the purpose of the mission. You can see from the animation, when you have a strong solar storm, it actually even affects the Earth's magnetic field, maybe compresses it, which is part of the thing that gets interaction when you have very strong solar storm. So let me go back one. What too far? Yeah, here we go. So in severe space weather, you have a number of events. You have solar X-rays that arrive pretty quickly, about 8 minutes, and they could last for minutes to hours, and they can affect some things such as radio communication navigation. And you have solar energetic particles that maybe arrive in 30 minutes to 24 hours and could last several days, and they're more serious. And then you can have really severe corona mass injections, which would arrive maybe 1 to 4 days, but produce very strong geomagnetic storms. And it's interesting that these various solar events that you see viewed on here don't necessarily, as a matter of fact, they're not necessarily related. So here's sort of looking at the sun, and you can see these solar storms and happening over the course of several days, but you don't get the same reaction from each. But if you see there's a very strong one, and relating that the events that occurred prior to the very strong event are not necessarily known. And so this is the sort of thing you'd like to be able to understand better through the instrumentation and maybe having multiple satellites. So I'd mentioned they're all 6U CubeSats, and here I am holding a model of the Cusp satellite. Again, 3-axis stabilized platform with the same sort of avionics that you've seen on some of the other small satellites that I illustrated earlier as examples. You have deployed solar arrays. All the CubeSats use solar for electrical power generation. Since this one's going beyond Earth orbit, it uses a more deep space X-band type transponder in order to communicate the telemetry back to Earth, to the ground stations. And this is a bit unusual for a CubeSat. This particular CubeSat is going to have 3 scientific instruments: an ion sensor built by Southwest Research, an electron and ion telescope built by Goddard Space Flight Center, and a vector helium magnetometer built by the Jet Propulsion Lab. So it's pretty unusual to be able to get 3 pretty capable scientific instruments into a CubeSat, a 6U CubeSat. So it kind of illustrates maybe what we can see in the future as we continue to miniaturize and improve the capability of these instruments. So these are the three instruments again, and they're in each case. I know, for example, the SIS, which is the one from Southwest Research, Super Thermal Ion Sensor, is essentially a downscale version of a much more capable instrument that we've used on other missions. So they're very, very capable instruments. So again, the idea is that you got more bang for the buck. I don't expect you to read this chart, but the main thing that I kind of wanted to illustrate was that it targets very high value science. They're leveraging heritage designs. The parts program are tailored for much shorter duration missions. Like this mission is just going to be a 3-month mission, as opposed to a mission that lasts months or even years. So consequently, you can get by with the lower cost type parts. And these lower cost and higher risks are very typical of CubeSat type missions, where you can accept higher risk. So again, want to point out that the size of these instruments is very small. Typically maybe 1U or 1.5U, and the mass is very small, less than 1,500 kilograms. Grams, 1.5 kilograms in each case, and very low power. So very high performance at a very greatly reduced size, weight, and power. So the Cusp mission is kind of like, just as we've shown you on that more detailed chart, it gets deployed. Then you have to go through commissioning, where you deploy the boom and deploy the solar arrays and so forth. And then you can begin your science. And you notice the timeline here: launch plus 10 days, launch plus 12 days. So 2 weeks after launch, you begin the scientific mission, and I'll show you what that is in a moment. And then the nominal mission ends about 2.5 months after launch, and there's a possibility for an extended mission, but it's kind of constrained by the power and the telemetry of data back to Earth. So initially, Cusp was supposed to be deployed. I talked about those bus stops. It was going to be deployed at the last bus stop, or BS5, and that would have occurred after the lunar flyby of the ICPS. But the lack of budget to analyze the ICPS stability after its primary mission was complete resulted in a risk that the deployer batteries, the batteries that operated that spring or actuated that spring deployer, could be too cold to operate much beyond bus stop 2. And that would have been a total failure for the mission. So now, a change in mission, the Cusp satellite will be deployed at the second bus stop, which is basically, bus stop 2 plus 2 hours. And this is sort of the risk you face when you are a rideshare mission. You don't control always the deployment and whatnot, but it also illustrates that you need to be prepared for these changes as you design these types of small satellites. And consequently, it does require resulting change in the operation. The attitude of the ICPS at bus stop 2 is unknown. So depending upon the deployment angle, the Cusp will drift toward or away from the moon. And the drift rate is such that there's a almost 30% chance that it could impact the moon. And so initial analysis indicate that there's going to need to be a lunar avoidance maneuver. And it also needs to make its first tracking contact as soon as possible. So this basically highlights the need to have pretty good design margins to accommodate these sorts of changes for the unknown as you get into these types of missions. So it's always something to keep in mind. Leave plenty of design margin. Be prepared for changes on the fly, so to speak. Now, in order to conduct the scientific mission, it has to be oriented in a very particular direction, because it's mostly looking at these high energy particles that are coming in on the solar wind. And the solar wind, the heliospheric current sheet, comes in a form of what they call the Parker spiral, and the Parker spiral is where the polarity of the sun's magnetic field changes from north to south. And it's kind of illustrated in this diagram right here. So essentially, these charged particles are flowing out away from the sun on this sort of spiral. I guess you could almost call it a dress spiral type sheet. And so you really want to be able to orient the field of view of your instruments to be able to intercept these particles coming in on that spiral type path. So that's an objective in order to be able to accomplish the scientific mission of the satellite. And consequently, the command and data handling, as well as the attitude, data, and control, have to be able to do that. So the computer or the data handling system for the Cusp mission is a downsized version of the bus itself is a downsized version of one for deep exploration. It's, again, 6U. It's got the same sorts of subsystems that you've seen earlier as I've gone through various satellite type configurations. And this particular bus for this Cubesat mission was presented at the Aerospace conference in 2016. So if you want to go learn more details about the bus itself, you can go to the proceedings from the 2016 Aerospace conference and learn more about it. The system overview, so you got the mechanical, structural, and thermal subsystem. You got the command and data handling subsystem, which is a reduced version of the same computer that we saw with Cygnus. Electrical power from the solar arrays, X-band transponder with the antennas. In this case, you're not using a dish antenna, you're using patch antennas. And it's got a magnetometer like that Juno mission. So in this case, you have to put the magnetometer down here at the end of this deployment arm for the high gain antenna. Again, getting it as far away as possible from the mass of the satellite. And another thing that's a little bit unusual about the Cusp satellite is it actually has propulsion. It has cold gas thruster, and it's not used for much in terms of attitude changing. It's mainly used for inertial shedding, because the primary method for attitude determination is from reaction wheels. So I'll show you more about that in one moment here. Oops, going back. There we go. So this is the computer, the Satur Computer. It's a Spark 8 processor. Again, it has the CCSDS communication protocol handler, and it's based on that Centaur design, which was used on Cygnus, and it's been reformatted for the Cubesat configuration. Auxiliary subsystems, the electrical power is provided by Clyde Space, 8 solar panels, 2 40-watt-hour battery packs, providing this type of voltage along with that peak power sensor that I mentioned earlier. 3 axes. Now the attitude determination control system is a single module, the XACT provided by Blue Canyon Technologies. It's an integrated system with 3 reaction wheels, the sun sensors, and the star trackers. But in addition, again, since this puts inertia into the satellite, in order to shed the inertia, you have the micro propulsion system from Vaco Industries, which uses 4 gas thrusters, and there's direct interaction between the Blue Canyon XACT and the Vaco MIPS in order to do what you need to do without having to engage the central data processor unit. Telecommunication Systems is pretty much the same baseline for all of the Artemis Q1 sats. It's using the IRIS V2 Deep Space X-band transponder that's provided by JPL. There's a whole issue describing these telecommunications in the April and September issues, in particular of the Systems magazine. So again, telecommunications in space is very tricky, and the link margins are very narrow and essentially dictate the distance from the Earth to the Moon that you're still going to be able to communicate. Challenges, there's technical challenges associated with miniaturization, heritage of designs, noise, and there's launch delays and uncertainties. Originally, we were planned to launch in December of 2017, but now it still hasn't launched. It's scheduled to launch maybe sometime later this year or next. That sort of delay impacts your staffing continuities and budget. There's change in deployment and operations that I illustrated earlier. And because the Artemis, the SLS is a human type system, even though there's not going to be humans on the Artemis mission, you still have to ensure that the satellites do no harm to either the rocket or the crew vehicle. And that means that you typically go through more reviews, more safety analysis for manned type missions than you do for unmanned missions. And so that was a challenge for the Cusp program. Current status, here I am with the Cusp in its holding fixture. We're just wrapping up system integration, getting ready to deliver it for installation into the system. Artemis 1 launch again, perhaps fall 2021, but subject to change. In general, Cubesat challenges are, again, small, not much money, low budget. You got the form factor constraints, the size, weight, and power constraints. There's not a robust amount of commercial off-the-shelf equipment, so consequently, these are early designs, early specs, so you have quality issues, part failures, schedule delays, especially now during COVID. We've had a lot of schedule delays on parts, as the entire industry has. So lots of things to work, lots of things that could go wrong. But in the future, I think you're looking at possibly more Cubesat opportunities for propulsion, like the solar sails or other types of electric propulsion. You got further opportunities for size, weight, and power reduction and attitude control. You got the radiation considerations when you go from LEO to deep space environments for the short versus long duration missions. Lots of opportunities in electrical power systems, better solar panels, higher energy to mass, and better ways to optimize the attitude control such that you still have your solar panels facing the sun, but still can configure your instruments to perform their science mission. And communication constraints, limited power, desired data rates, novel designs, and so forth. And so that's the presentation, and we're about 1 hour and 20 some odd minutes into the time. I see there's been a few things in the chat here. Says the first. You want to read those, Victoria?
Yeah, we have some questions actually from the YouTube live.
Valentina?
Yeah, we have
Yes.
some. So I'm gonna start telling them, okay? So
Yes.
Victor Macias asks, how different nations in Latin America have contributed in aerospace sciences in the last decades?
Oh gosh, a number of them. We frequently collaborate with several countries in the European Union. There's the European Space Agency, and so we often have partners from the Europe. Japan is a big contributor to space missions that are either NASA missions, or sometimes we partner on missions out of there. So those are big partners. Sometimes from Canada. I'm not familiar with many missions from Region 9, so maybe that's a potential growth area in the future.
Yeah, for the next questions, I will be translating simultaneously, so you can say like a sentence and I can translate it, okay?
Okay.
Thank you so much. Christian Vasquez asks, why does the high electricity of an orbit reduce the radiation the satellite sees?
Because it reduces the amount of time that you're in the high radiation field. When you're close to the planet, you're in a high radiation field. When you're far away, you're not in it. So it reduces the amount of time that you spend in the high radiation field.
Okay. Es porque reduce el tiempo en el que se está en el campo de radiación. Entonces, pues, como se reduce el tiempo, es la razón por la que ocurre este fenómeno. Okay, we have another question. Diego Chavez asks, what is the biggest challenge for emerging Latin America space agencies?
The biggest challenge for what in space agency? The biggest challenge for merging Latin American space agencies. Yeah, good question. I think the biggest challenge may be to essentially develop a private industry that you can use, because the fastest growing element in the U.S. are the private organizations that are building launch systems. So I think that's where we should look for the challenge in Latin America, to develop the similar types of commercial-based organizations that can conduct these lower-cost, higher-risk missions.
Vale, entonces él piensa que desarrollar una agencia de este tipo es más conveniente buscar como el tipo de agencias privadas, ya que estas son las que son más exitosas en lugares como en Estados Unidos, y es donde debemos ver los retos, y pues aquí se puede ver como esa parte. Okay.
And furthermore, I think that since when we go with private organizations, we don't necessarily have to deal with government regulations and so forth. So it becomes an easier opportunity to work with a private organization than with a government agency sometimes.
Y a veces ocurre que es mucho más fácil trabajar con agencias privadas, ya que no tienen que ir como por las leyes gubernamentales. Entonces, pues realmente es pues como que se torna en una situación mucho más sencilla. Okay, the next question is, how satellites can integrate with other elements on the surface as rovers, as unmanned aerial vehicles?
Yeah, we're seeing that right now with the Mars, right? They've got the small unmanned aerial system that was attached to the rover, and it was kind of interesting. I saw earlier that they're having difficulty because dust covered the solar panels of the unmanned of the rover. Consequently, it could not be charged. But the notion of carrying a small robot on a on a larger platform is certainly something that has been done and will continue to be done.
Ok, entonces pues se ve hoy en día que, por ejemplo, con lo de Mars, pues que el sistema fue lanzado con un rover, hubo algunos inconvenientes, por ejemplo, que los paneles solares fueron cubiertos por polvo y pues por ende el robot no podía cargar. Pero pues esta va a ser una realidad que va a seguir ocurriendo en proyectos hacia el futuro. Okay, we have another one. Paula Rosero asks, besides the power system, what will be another limitation in space missions?
Radiation is always a limitation. Telemetry, again, the speed, the telecommunications, I think is a limitation. So those are in addition to power. So radiation and effective communications, because again, I think as we go smaller, the ability to reliably communicate, that you don't put all of the processing on a single node, you distribute the processing. So having a very good communication between nodes in a constellation or mesh is really a key technology.
Okay. Bueno, pues adicional a la energía, la radiación siempre es una limitación que se presenta en este tipo de sistemas, y adicional a ello, pues encontrar un sistema efectivo de comunicación. Igual, pues digamos como que las máquinas están construidas no de un nodo sencillo, no es uno solo, sino que pues está compuesto de muchos sistemas que interactúan entre sí. Okay, thank you so much. Jesus Gurute asks, how much does it cost to send a CubeSat to space, and what entities are in charge of it?
So, CubeSat missions can be, there's a whole series right now that each mission is $20 million or less. Now that sounds like a lot of money, but it's much less than 500 million or 1 billion. So, right now you're seeing CubeSat missions for under $20 million. And again, so the funding can be funding can be provided by government agencies, but $20 million is within the reach of private organizations. Some large universities spend that much money to conduct research, so it's even within the reach of large universities. And the price will go down as the technology matures, and you get more different providers of launch systems.
Okay, thank you so much. Okay, las misiones de CubeSat están rondando alrededor de 29 millones de dólares o incluso menos. Realmente es pequeño. Es pequeño porque usualmente ese tipo de misiones pues cuestan hasta billones de dólares, y pues las personas, digamos como que las organizaciones privadas tienen este presupuesto usualmente para hacer investigación en sus instituciones, y adicional a ello pues digamos también puede haber como agencias gubernamentales que estén dispuestas a hacer. Okay, and we have one last one. So Isabella asks, what are the difference between commanding a regular satellite and a CubeSat from the ground control? Is there maybe any particular difference regarding the control software?
I think the main difference is, again, that on CubeSats, and this is true on large satellites too as well sometimes, but one thing on CubeSats right now is that the instruments are always fixed. There's no gimbal on the instruments. So in order to conduct the science of the mission, you have to have the satellite, again, oriented to make its best observation. And consequently, often while you're doing that, you can't communicate at the same time. You can't do the scientific measurement and communicate. And so the challenge you have is that you have to sort of pre-program maneuvers to do the science mission and then maneuver back to do the telemetry. And so you're much more constrained in those operations, but just simply because of the limitation, the inability to do both functions at the same time. That's the big challenge.
Okay. Los instrumentos de Cubesat usualmente ya están como bien definidos, entonces pues se pueden comunicar al mismo tiempo pues que se están realizando el resto de funciones y puedes como preprogramar la máquina para que un componente como que se encargue de la telemetría y otro componente se encargue como de la comunicación. Entonces realmente es algo que se puede hacer y se puede como programar. Okay, so there are all the questions that we got for the YouTube Live. Thank you so much, Mr. Downing, for all your contribution today. It was a really interesting talk about CubeSats and for having shared this space with us. It has been a really nice space. We hope that it will be a great motivation for all who have attended, and we hope that spaces like this can continue to be open in the future and you can be part of them.
Well, I enjoyed it very much, and I appreciate everyone that attended. And I think most of you are students, and so I wish you very well on completing your education and very good success in your career. And I hope you will join Aerospace Electronic Systems Society.
Yeah, it is what we intend to do. Thank you so much.
Thank you. Have a good evening.
You too.
Goodbye.
Con esto damos por terminado.